This one, well, the previous one I think was NTT in Japan.
Why do we think 25 terabytes is very much?
But then you look at 25
Look at
terabytes.
relative.
This is one small CMTS in some location, not even Tokyo.
Okay, so it's not one carrier. That's what I was trying to get at.
No, so this is not the total traffic for the carrier. This is the total traffic for one little hub for one carrier.
Still not. Okay.
This depends on the location you're talking. Big metropolis versus small location, and so on. And this is just a conglomerate.
Anywhere you go, if you have one pop of a carrier that carries 25 terabytes of peer-to-peer traffic in 1 week, you just do the math of to run this kind of capacity, how much the actual transport equipment will cost you, and what it will cost you to keep up with this. It's very expensive.
Well, you should be charging for it.
Yeah,
That's the point.
Yeah, that's the whole point. That's why he's here.
Exactly. That's the point.
I didn't even mention, by the way, where a lot of those guys hurt the most. And it's not in accumulating all this access equipment. The biggest pain is in the transit. You look at Japan, if they need to carry traffic across the Atlantic, and peer-to-peer is distributed, so there's no localization. There's no reason to assume that if you look for Nemo, you're going to find it in the same town.
Right.
All of this traffic, we're sitting a lot of transit connections. Those transit connections, not surprisingly, they look the same. 70% of the transit connections peer-to-peer, a lot of those get charged by the megabit. So even charging, one of our original ideas were, one of the packages you could offer is an all-you-can-eat peer-to-peer for a premium. We said charge $20, $30, $40 of a premium and let those users, and at least you get something out of it. We had 3 of the carriers come back to us, say we did the math of what it would cost us to provision an all-you-can-eat peer-to-peer. All 3 numbers came in between $800 and $1,000 a month to break even on a single user. So that blew the all-you-can-eat idea. There's still, you can have more peer-to-peer for some premium, but it can't be unlimited.
So they're extremely lucky that probably a very small percentage of our population actually uses all that network.
You know, that used to be true, but that changes too.
A lot of 15-year-olds out there.
Well,
One of our old ladies getting old stuff.
Right. When we started looking at the network, 90-odd% of the traffic was generated by less than 5% of the users. With peer-to-peer, that's no longer true, because more and more people have discovered this and leave their computers on all the time. And those are the big traffic generators. So now you look at the demographics, it's probably 35% of the users generate the large amounts. And P2P, I think, is going to be a way of life. So you better deal with it. In terms of this is one of the carriers where they actually try to monitor the experience. So they said, after a while, they said, we want peer-to-peer traffic to be cut by half. So they set a limit, and they said, we don't want more than 30% traffic, peer-to-peer traffic on our link. We don't care who it's coming from. And this is what happened here, and then they started monitoring the end-user experience. It's hard to see in this resolution, but there's a lot more of this light blue and video gaming, instant messaging, which didn't exist almost previously because you couldn't get it done. Suddenly started taking off, so after a few weeks of monitoring this, they liked it so much, they took the overall P2P constraint even further down. And all this time they were monitoring end user satisfaction. The first indication was they showed us this graph of calls coming into their call center saying your service sucks. And that was a way of life for them. Those were hundreds of calls per week. And about this period when they started controlling peer-to-peer, the graph dropped to 0. Not to a low number, to 0. People stopped complaining. They had a couple of calls later on from some of the heavy peer-to-peer users saying, we're not happy, and they toasted, they broke up in the champagne. They were happy. They said, if those few users went out to a different network,
Yeah, right, great.
They're saving their money.
And make the other people come over to them.
right.
What is the x-axis? Because I have a question on the spikes.
Time.
time I know, but that's understood. But what I'm talking about is it each graduation there is that they see what I want to understand is between the spikes, what is the time duration? They all look equal. Are they daily?
So, overall, left to right is a span of several weeks. I
Okay.
don't remember what exactly
Okay.
those ticks
No,
were.
I'm asking between those spikes there.
So it's 24-hour spikes.
It looks like it, isn't it?
Are those 24 hours?
Yeah, probably.
Yeah.
Okay. So there's a particular time when this happens. Peak happens.
I think the peak patterns are morning before kids go to school, basically, where they check what's been downloaded over the night and start 10 new ones.
Okay.
And then in the evening you come back and say, ooh, we've got 3 more, let's start 5 more.
Okay.
Or people in some HP cubicle coming in the morning. Last of those slides is just more conceptual again. If you look at the way ISPs have been adopting this, first stage is let's look at our traffic. Second stage was, oh my God, we've got to control it. Third stage was, wait a minute, we have the tools to control it. Can we free up some capacity dedicated to voice over IP now and run a service? Can we free up some capacity for video on demand and get somebody interested to stream over our network? Can we go to Sony PlayStation and say, we'll give you PlayStation 2 capacity and you can use really good gaming on our network for a premium? Start creating those revenue sources.
After looking at this, I'm thinking that what did not happen, bandwidth trading, you have heard about that, you know about that,
Right.
and that may come back. Looking at this, bandwidth trading never happened. Although infrastructure was there.
Right. There is some amount of bandwidth trading going on. There's a futures market, but it's not interesting.
No, this small thing. I'm talking big time.
Yeah. I think this will make it more interesting. It's a bunch of ideas of how you can differentiate and create some more interesting services. The first example is, I'll just go through the first one. All the differentiation that broadband providers have used to date is based on how many bits per second they serve you at home or in the office. And it's the only mechanism they have, but it's not a good mechanism because even for somebody fairly technical, if you get a 384 kilobit upstream, 128 kilobit downstream package, or 256 upstream, 76 downstream, you know the first is better than the other, but how much should you pay more? Is this like $3 a month, $35 a month? And either way, you're not going to get those speeds because everything is congested. So you can't expect to get them on a sustained rate 24 hours a day. We're trying to get this to be at the application level. So for example, one of the things we've helped implement is for some of those broadband carriers who try to address dial-up users. So they say, we'll give you a package which is priced at a slight premium over dial-up. It will give you the full broadband experience of email and web. And everything else will limit it to be dial-up-like. And so if you're not sure dial-up or broadband is pretty much the same price, might as well get great browsing. But now if you want more than that, you better step up to the regular package. You get pretty much good everything. And if you're a die-hard gamer, there's a premium gaming package, and we'll give you some great connectivity for your gaming application. We'll pick it up in the network, we'll provision it, we'll help bill for it, we'll control it. So a little bit about the platform and some of the issues it has to deal with, and a little bit about how it does what it does. So we talked about ports not being enough. You have to have some, or 2 dimensions basically, the application dimension and the subscriber dimension, and put them together. I think I mentioned this, but a lot of those peer-to-peer protocols use port hopping, use masquerading, use a lot of techniques to try to look like something else. So you have to be fairly deeply engaged with the traffic. So 3 principles were underlying for the design. One is it's got to be stateful. You've got to track the application throughout its duration to figure out what it's up to. Otherwise, you quickly lose sight of what's going on. If this application negotiates something else on some new port, you didn't pick that up. Whatever goes on that new port, you're completely in the dark on. Second is programmable because with Skype, we support close to 30 variants of peer-to-peer. There's new stuff getting deployed almost every week. So if this thing is not programmable, by the time you've deployed it, it's obsolete.
Who programs it?
Sorry?
Who programs it?
We do at this point. But again, I'll talk about the language a little bit. The grander vision is the language that we've put together to make it just easy to program. At some point, we think we'll just put out in the public domain. And it's an abstraction. You can create your own services, compile them down to your favorite device, or to the intelligent service devices you have. Hopefully they're PQ. And deploy new capabilities in your network. Shouldn't be done by us. Conceptually, there's a hardware layer, which I'll talk about a little bit. Then there's an operating system that creates abstraction, hides all the hardware details. And then you can write different applications for it. So we've written 3 so far. One is Insight, which is just for analysis. And it often gets resold as part of other companies' mediation systems like HP's. And then there is Engage, which helps control, and we've created an application for the wireless space, which helps implement prepaid. Again, the same concept. If you know what the application is and who the user is, and you can meter it, then you can easily implement a model where a mobile carrier sells you 100 minutes of gaming. When those 100 minutes are gone, you're blocked for continuing this gaming session. You could probably still do all the other things as a regular user, but that gaming package is gone. To do that, you have to sit in the traffic, pick up the gaming session, know who the user is, be able to monitor it, meter it, control it. So from the 2 big challenges that we faced, one was essentially the hardware. We live in a stateful world, so if you look at a high-speed networking environment, say gigabit or an OC48 type connection, and you look at how many cycles of processing you have per packet, even the task of a packet comes in, match it to 1 of a million contexts, bring that context into memory, do nothing, write it back, and get ready for the next packet is hard to do in the number of cycles you have available if you want to maintain wire speed performance. And so we've had to come up with a fairly sophisticated CAN-based architecture to be able to quickly find those states, bring them in. And that's where the game begins. The second phase is you have to classify traffic. And we've created an architecture where there's about 5 different chips that we have had to put together, and then a bunch of high-end RISC processors that give us full flexibility. And there's some issues that quickly come up because from a performance standpoint, either this is a completely shared memory architecture, which doesn't scale in terms of performance, or you have to make sure that every flow in its entirety, if it has to be dealt with by a processor, all the packets in the same flow will always go through the same processor. So you need some intelligent load balancing to make sure this architecture really scales. And once it does, you can have more and more processors and get more and more performance. A lot of the shaping, queuing, metering, there's a lot of activity. That's another hardware component. Yeah.
Can you detect a SYN attack?
Interesting question.
Detect a what?
A TCP SYN attack?
Yeah. So
Denial.
denial of service is not where we focused when we built this, but at some point we realized since we already profiled the traffic into flows, some things are really easy for us to do. SYN attacks is one of them. And in fact, our hardware implements some of the TCP state machines hard-coded because of performance. But things like looking at, don't even care about a flow before the first SYN-ACK. Don't care how many SYNs you have. In fact, we can throw them all away, and nothing bad will happen. Immediately helps mitigate a lot of those SYN flooding attacks. And I've personally been amazed since we've started getting deployed to a lot of places, how much of this stuff is going on. I wasn't aware, and by the way, ever since the 9/11 and ever since